Well, so today's topic of discussion is single phase induction motor, and if I do not mention it otherwise, we will consider the rotor construction is just like a squirrel cage induction motor. Now, let us consider two situations very much categorically. One is what would happen if we try to start a three-phase induction motor with one phase disconnected from the supply. And second one is that repeating the same experiment with the electrical part, but only difference is that here your machine was in standstill condition. What would happen if fuse of one phase blown out during induction motor operation? So these two clearly indicates two extreme cases. This is like it is known as single phasing of three phase machine. Now, what would you observe if you separately try to carry out these two experiments by external artificially created experiment? You will see that in case of first one, the motor will not start, rather it will draw a very high current, and you can keep on applying or means increasing the voltage applied across the stator terminal of the motor. You will be ended up in burning out the windings without making, you will not be able to make the rotor run. But in case of the second one, what you will see that it will give you, the motor will slightly slow down, but it will continue to run in the same direction. So, if single phasing is a problem, the two experiments that I have stated and also their observation, it makes it very clear that for closed loop, for a motor that is already in run, what we are going to experience, and the motor that is in standstill condition, what we will observe, these two are completely different things. Normal extension of logic implies if one is running, then the other should also run. Even we can expect that for this first condition, when the one phase is disconnected and we are trying to start the motor would run at a slow pace and drawing a high huge amount of current. But here the means completely different striking observation we will make is that the motor will not run in case it is in standstill condition. However, one thing that is also very interesting, and we should mention it in this context of first question, that the motor will start running in a single direction with this condition, like two phase wires are connected with supply and while one is not connected. If you, by means of some external force, suppose by means of your hand, if you allow the motor to rotate in a particular direction, whether clockwise or anti-clockwise, the motor will rotate to that particular direction. Now, that is another striking observation. Like if you perform two experiments of condition 1 and name them run 1, run 2. In run 1, you apply external torque in clockwise direction and you will see that the motor will start rotating in clockwise direction. And if you perform run 2, applying torque in counterclockwise direction, you will see that motor is running at counterclockwise direction. So what makes the motor to run in that particular direction? Generally, for a three-phase induction motor, what we observe, if we change the phase sequence, then only it is possible for us to change the direction of the rotating MMF, and so we can reverse the direction of the rotating motor rotor. But here what we are observing, that the rotor is changing its direction without having much to do with our electrical connection. You maintain the same electrical connection at its input port, but just to, if you change your external force application direction, the motor starts running in different direction. So to investigate all these very striking observations, or those observations you can also make if you get chance to perform this kind of experiments. That makes it very okay. One thing I would like to mention, I already told it to Angshuman that I have been seriously suffering with illness, and I am not even at this moment I am also not feeling good. So I am trying my best to complete it as soon as possible, but I need your cooperation. Okay, so what is here that we can explain this working of single phase induction motor using double field revolving theory. What double field revolving theory states, before going to or making it much more complicated, let us try to analyze the case, what would happen when we are having so okay. One question that may comes in your mind, that as of now I was talking about two-phase construction, but telling it like it is your like these two phases are present and they are the third phase is not connected. Then first of all, let us make it very clear that these two are going to produce similar effect. How? Let me explain it to you. If this is only present, then this will make a force field like Am cos omega t cos alpha. At an angle alpha, if you try to find out, you will see this is the component. What would happen if we try to find out here? It will give Am cos omega t cos alpha. These gentlemen, if both of them are carrying equal current, this will produce Am cos omega t minus pi by 3 cos alpha minus 2 pi by 3. Here also 2 pi by 3. If you add them, what you will see that unlike in a balanced three-phase case, you will have an oscillating just like this one. This is representing an oscillating one in this way. It is, try to understand that this is not space varying. This is a constant space invariant time varying magnetic field, and if you do it for this case, you will see that it will also produce the exactly similar result here. Correct? So these two will produce the similar effect, and however, now just a minute. If we try to analyze, so analyzing this and analyzing this actually are same, and no further advanced treatment is required when your two phases are connected. They are basically representing the same thing or same situation if your one phase is only connected with the system. So I would like to consider a situation where only one phase is connected, and here if this is an angle alpha, then we are getting Am cos omega t cos alpha, that could further be written like half of Am cos omega t plus alpha minus omega t, or you can write it omega t minus alpha as you wish, because this is a cos case, plus half Am cos alpha plus omega t. So both of them are having equal value, and how you can visualize this alpha minus omega t, it is trying to traverse in forward direction, and alpha plus omega t, it's trying to traverse in backward direction. So this is a very interesting case. Therefore, the net MMF that is not rotating in the space, that becomes constant with respect to its space position, but it is oscillating in time. Now, as we know, for the forward rotating this one, the amount of slip will be ns minus nr by ns, that is equal to s, and for the backward rotating it will be ns plus nr by ns, that will be 2 minus s. Now let us consider a situation like this. positive angle, and our uh, field is that backward rotating field is in clockwise direction, right? Now here you can see that let us consider the machine is having two winding. This is our main winding. For the time being, let us consider that both windings are identical in nature. Both of them are having equal means RL ratio and everything. Only the auxiliary winding is 90° ahead in space. And also the current that you are going to send through this is that the auxiliary winding current leads the main winding current by an angle of 90°. So if I have to draw a phasor, I would like to draw something like this. This is our IM, this is our IA. Clearly IA leads IM by an angle of 90°. This is a balanced case. In case of unbalanced operation, you can have IM and IA, they are not exactly in quadrature, and in case of your single phase, it will be just only one particular IM is present, right? Well, so now let us consider that the IM and IA are identical. When IA is equal to 0, the winding will behave like a single phase machine. But let me start with a very simple set of arguments so that you can understand the subject. It is not my objective to make you confused or means increase the amount of confusion that you have already means you get from after reading different books. So how I would like to start? I would like to start with an approach of balanced and symmetrical component systems, forward and backward. So let us consider for each of these forward rotating MMF, we can associate forward rotating voltage, current, induced EMF, everything. Now, however, forward and backward rotating components are not accessible to us from our outside terminal. What is accessible to us is that something like our equation of main and auxiliary winding. If you note how I can write in this way, then you must understand that how they are placed. The auxiliary winding is leading the voltage by an angle of 90°. The IM by an angle of 90°. Now, here it is IF, IB, and here it is JIF, and here minus JIB. Why so? Because if you consider this one, it is when you are trying to move in this direction. Why it is minus JIB? Let me make it very clear. When you are doing it, you are moving in clockwise direction. This is your backward. So thus that EMF must be minus JIB. Here if it is IB, when you are rotating in this way, it is 90° lag. And that is why it is minus JIB. And similarly, when you are talking about forward component, this must be plus JIF, because clearly IF, the forward component of auxiliary winding, is leading the forward component of main winding by an angle of 90°. Now with this, what we can write is something like the main and auxiliary winding developing rotating MMF in the forward direction, and the components IB and minus JIB in our main and auxiliary winding. So what we can write from these two equations, IF is equal to Im minus JIA by 2 and IB is equal to Im plus JIA by 2. Now the voltage equation that we can figure it out from this one is that the impressed voltage is just like what we observed in case of our transformer. Voltage across any stator winding is the sum of the phasors of resistance drop, leakage reactance drop, and the induced EMF due to air gap flux. Now, if we are assuming that it is, as we have assumed that both the windings are identical in nature, so let us consider both the windings are having R1 and X1 as resistance and leakage reactance, and thereby we could write the equation like Vm is equal to Im R1 plus Jx1 plus Em, and Va is equal to Ia R1 plus Jx1 minus plus Ea. Now here again this Em and Ea, we must consider the presence of Ef and Eb in this Em and Ea. Following the same notation, or rather not notation, rather same convention what we did for our current representation, we can write the Em and Ea like Em is equal to Ef plus Eb and Ea is equal to Jef minus Jeb, right? So if this is the case, then what we can write, it is like Vm is equal to Im R1 plus Jx1 plus Ef plus Eb, and Va is equal to Ia R1 plus Jx1 plus Jef minus Jeb. So this gives Vm is equal to Vm minus Jva by 2 and Vb is equal to Vm plus Jva by 2. Now, considering all these, what we can do is that from this one and this, we can write our equation to fictitious equation. See, Vf is not directly measurable, but we can form this equation like so. These are very important equations. So now I am going to draw the two set of circuits for this forward component and backward component. What we can draw is that R1 and what about the other part? Other part is IB. So the net torque will be how much? As we are considering it's a two-phase case, so this should be multiplied by twice. Now this is in synchronous watt. Now what happened in case of means machine? As we know that IA is equal to 0 for a single phase machine. So at the onset you will have we will have this condition. Now here let us just draw. Now with this equation let us draw the circuit for our single phase system. What we will get? Let me draw it in the next page. Here it is IF dash and here it is IB dash. The way I have connected them, clearly here you will get IF and that is same as IB. Now see, during start, if you do not allow it, then what will happen? Your S is equal to 1. See the amount of torque, both of them will cancel out and this circuit is perfectly identical. The upper and lower half of the circuit is perfectly identical. But once you apply an external torque, what would happen? In a particular direction, it will reduce to a certain value, say s is equal to 0.5, or means 0.5 is to means low value of slip for an external input. Say you can make it suddenly due to application, you make it 0.9 or something, but that would give you a slightest torque. Oh God, that will give you some additional torque in this form. So if you see this equation, it becomes very clear that your net torque is now not is equal to 0. So this perhaps gives you an answer when the machine is already in run. If you disconnect one phase or one fuse of one particular phase is blown out in case of a 3-phase induction machine, how the machine could continue to run at a lower speed, because this is the case. The machine sleep is not is equal to 1, rather some value that is less than 1, and in which the forward torque dominates. And this forward torque, domination of this forward torque causes a slight acceleration, and this acceleration would be sufficient to make the machine now when the machine accelerates, what would happen? The slip further falls below to its previous value. If previously it was 0.9, now due to this additional torque it will become 0.85. Now when it will become 0.85, you can easily understand that the forward torque, the difference between forward and backward torque will increase, and gradually the machine will build up speed. And once it reaches close to its synchronous speed, and we know that we can continue, means we can change this range of stable operation. If you can somehow manage the value of R2 small, you will be able to see that your machine means stable operating zone is very close to s is equal to 0 to some very small value of slip. Your machine will operate. Your stable zone will be confined. So does your this machine, when you make R2 dash small, the machine will accelerate for even if you are having a single phase winding and giving one phase supply, and it will reach to that particular condition where it reaches your steady state condition. And at steady state, very close to 0, you can see that this value will be very, very large, and this one will be very small. So what would happen in reality, that this will produce a huge amount of torque. Now if you think that like, why so? Because the current that is flowing through your R naught plus Jx naught means this backward circuit is connected in series. So if we apply or reduce the value of series connection, and it is connected in parallel with this one, so if this one builds up resistance, then current flow through this part will means reduce, and accordingly here means the IF dash will be means gradually IF dash will be becoming small and small. If S is becoming small, gradually IF dash will face more and more resistance. So obviously one question may comes in your mind that it will change the torque pattern, and what you can expect that this IF dash may flow through here and gives you more and more torque while you are having here. Now this is a very tricky situation to understand that these two circuits are connected in series, and if you consider the magnitude of R naught and Jx naught for a ergonomically designed circuit, the value of these two must be sufficiently high. So you cannot expect a boom, or means not boom, rather overshoot of torque due to this I2 IV dash, because if IF dash falls below limit, or if IF dash is becoming small and small, it is bound to affect the magnitude of IV dash. So that is a very important understanding, that R naught and X naught are very large value, having a very large value. The main current path is R2 dash by S Jx2 dash and R2 dash by 2 minus S Jx2 dash, and they are connected in series. So if you do this, there is a very means, even if IF dash is getting affected due to means change in slip, IV dash is bound to get affected, and even it is facing or flowing through a molar resistance path, it cannot produce a tangible effect as long as the torque pattern is concerned. And well, for approximate equivalent circuit, what we can do is that we can blow out the R naught, considering this is very small in our working range. So R naught can be blown out, and this stator side resistances could be clubbed together to make it happen, right? However, here you can see that the current is becoming half due to all the circuit parameters, they are appearing twice. So what we can do is that we can make the circuit parameters half to make the current is equal to Im. By how we can do that? So this is our correct circuit model. So let me redraw the correct circuit model once again for your So this is our circuit, right? So here, this is now obviously after this, the immediate question comes how to determine the parametric test. And for that, what we can do is that we can just consider somewhat what to say that an approximate equivalent circuit, that is like because the previous one is difficult for us to digest and use while doing the torque calculation and other. So what we can do is here that we can make a slightest modification and without altering the quality or the performance of the circuit, we drop R naught and have our we club this R1 JX1 and R2 dash with so this is the amount of torque, and this one, the whole equivalent impedance, we can say this whole equivalent impedance is ZF, and the second one is ZB. Of course, the real part of ZF is RF and real part of ZB is RB, and this gives us the power generated is the net torque obviously this is an approximate formula. But this approximation is good because this helps us to generate the formula that we can use to understand the amount of generated torque. And what about the mechanical power output? It will be 1 minus S, that is the value of slip, into T net. Now, after this, the obvious question comes that how we can determine the equivalent circuit model of our machine. The equivalent circuit model is just we do it using the same technique we did it for our three-phase induction motor. Only change what we are going to observe here is that it will be like R1 JX1 R2 dash JX2 dash, and here also R2 dash JX2. This is the equivalent circuit for block rotor test, and we know how we can figure it out. However, the open circuit test, or that no load test is something like just. So here what we will have in case of no load test is that something like the equivalent circuit is quite different than that what we used to get for three-phase induction motor. If you wish, you can incorporate R naught by 2 here also, but that would unnecessarily complicate the whole situation. So it is better that you do not consider this one. The equivalent circuit will become something like this is a pretty interesting one, and we can figure out the values of the circuit element. In my next video, I will discuss starting of three-phase induction machine and its other issues. Sorry, single-phase induction machines and other issues, and if possible, I would like to discuss a brief about linear induction machine, because that is quite often used in your levitating train, bullet train. All these catchy keywords are very good to hear, but it is no harm to educate ourselves to a bit of that technology. At least you should not have any kind of weird notion that means it is driven by some other motor. So for that, whether it will be a part of our exam or not, that we can decide it on the later course of time. But we must not miss any such important consideration while discussing on electrical machine, right?